All right, let's start talking about chemistry. So, in chemistry, it's all about the interactions between atoms. More specifically, when we're looking at chemistry, it's all about chemical reactions, which are based on electrons, which are one of the building blocks of atoms. All right, so we're going to break down a little bit of vocabulary and what an atom is made of, what everything is made of. All right, so first thing, atoms. These are the building blocks of matter. Okay, so you are made out of atoms. The air around you is made out of atoms. Everything you've ever eaten or drank is made out of atoms. The chair you're sitting on, or couch, or wherever you happen to be sitting on, it's made out of atoms. Basically, everything you've ever seen and interacted with is made of atoms, with the exception of light. Light isn't atoms. But that gets into photons, which is like dealing with other particles, and we're really concerned with these three: protons, electrons, and neutrons. These are what we call subatomic particles. Okay, so these are particles that make atoms, or particles smaller than atoms. All right, so sub means like a smaller group of. Okay, so subatomic, these are things that are smaller than atoms. All right, the three that we care about are these: protons, electrons, and neutrons. They have different properties, and they can be identified by what type of charge they have, what mass they have, how they behave. Let's talk about them. Protons. These are, as far as subatomic particles go, heavy. These are the big ones. This is where most of the mass in our atom comes from. Okay? These are also positively charged. So think about like a magnet, right? It has a north end and a south end. All right, when we're talking about subatomic particles, things can have positive charge or negative charge. If something has an opposite charge, it will attract. Okay, so if you have positive charge next to negative charge, it'll go together. Okay, so protons, they're heavy, they're positively charged, and they're found in the nucleus of an atom. So if we were to draw an atom, all right, it kind of look like Jimmy Neutron logo. Got a whole bunch of stuff in the middle, and then we'll have things flying around the outside. Now that is a very simplified and very outdated model of the atom. We're going to talk more about how the atomic model has changed over time as people have made discoveries, but that'll help us kind of visualize what's going on. There is a nucleus that is very heavy at the center of an atom, and then there are clouds of electrons flying around it. Hey, look at that. Electrons are our next thing. All right, so these are extremely light in comparison. Like millions of times lighter than a proton. They're tiny. And they are negatively charged. Okay? Whenever we're talking about chemical reactions, it's electrons moving around. Depending on what type of atom something's made of, it will try and gain electrons or lose electrons and make bonds in the process. We'll talk about that more later. Electrons are light, they're negatively charged, and they orbit the nucleus. Okay. One thing I do want to add to protons real quick, these determine what element you're looking at. Okay. So if you have an atom that has one proton, it is always going to be hydrogen. Okay. If you have an atom that has two protons, it is always going to be helium. If you change the number of protons, that would change what element it is. And people were really excited about that thought, changing one element to another. Whole branch of pseudoscience in the Middle Ages where they were trying to turn like lead into gold. Obviously they were unsuccessful because moving protons is extremely difficult. It's a nuclear reaction when something gains or loses protons. Okay? Protons are very difficult to move. Okay, so if you were able to move a bunch of protons off of lead to make it into gold, it'd be very impressive. It'd be a colossal waste of money, and you'd probably set off a colossal nuclear reaction. Don't do that. So protons, they like to stay where they are. Electrons, they move all over the place. They're light, they are on the outside of the nucleus, they're free to move from one place to another. The weird one is the neutron. These are the same size as a proton. Okay, so they're also very heavy as far as subatomic particles go. They're also found in the nucleus. Oh, I did a bad job with that E. There we go. Also found in the nucleus. The weird thing about these guys is that they don't have a charge, right? Protons are positive, electrons are negative, neutrons, it's right there in the name, neuter, like neutral, like zero charge, okay? So they have no charge. That's not to say that they're useless. Now, neutrons hold together the nucleus. We'll talk about that more in just a second, okay? So we've got protons, electrons, and neutrons. Those are our three subatomic particles that make up an atom, all right? And that periodic table that is in the Start Here file, and it is also in the file where you found this video, we'll have a lot of information about how to figure out how many of each of these an atom has, okay? So let's talk about that. Okay, so talking about the periodic table. Looking at one of these, it has a lot of information, okay? Each one of these elements will be found in a little box, okay? Let's say that we're looking at, how about, let's look at fluorine, all right? So fluorine is over here on the right-hand side. It's got an F right there, okay? Let's also put some numbers in there that are in this box. We've got a 9 over in the upper left-hand corner, and we've got 18.998 down there, okay? Now, if you're looking at a different periodic table, these numbers might be slightly different. This number will definitely be the same for fluorine. This number might be rounded a little bit, like they might round it up to 19, it might have less digits to it, but it will be roughly the same number. Also, depending on what periodic table you're looking at, they may move around in the box. Okay, so what we're concerned about is which one is the numerically larger number. Okay, so you may see a periodic table where the 18.9 is on top and the 9 is on bottom. That does not affect the information. You're looking for a larger number and a smaller number. When I say that, I don't mean font size. Okay, so for example, if I had like and a 50. Okay, when I say larger number, that's a bad example. Why did I put a 50? A 5, there we go. Stupid. Also, that looks like an S. There we go. So when I say the larger number, I mean the numerically larger one. 10 is a larger number than 5. It doesn't matter that 5 is a larger font size. Okay? I don't know why I have to say that, but people get confused when they look at things and they see a physically larger number. And they're like, that's the big number. No, that's the big number. Okay. I hate that I have to say that, but I have to say that. Okay, so there's a lot of information here just with that letter and those two numbers. Okay, so let's break down what we've got here. Right here, this is our atomic symbol. Okay, each element will have its own atomic symbol. Okay, if I write down just a capital F as a symbol for something, that is just fluorine. Okay, other things may start off with the same letter, like calcium or carbon or cesium. Okay, there are a lot of things that start off with C. All right, but you'll notice each one of those is different. They all start off with a capital C, but then lowercase letters after that tell you which specific element it is. Okay, so whenever you're seeing like a bond on something, like if we had capital C and a capital O, Bonded together, that's a carbon and an oxygen. A capital letter means we're looking at a new element. Okay, whereas if you see this, capital C with a lowercase o, this is one element. That O isn't capital. That means that that is part of the atomic symbol is a CO. That's cobalt type of metal. Okay, so keep an eye out for capital letters. That's telling you this is the atomic symbol for some element. Okay, lowercase letters are just saying this is part of that atomic symbol. All right, so atomic symbol, this tells you what element you're looking at. Okay, this number here, this little number. Okay, so the little number. All right, if you look at the periodic table, you'll notice as you go from left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. It goes up by 1 for every single element. This is called the atomic number. Tells you which element you're looking at. There's more information there. We'll get to that in just a second. The big number, okay, so in this case, the 18.998, this is the atomic mass. This is how much it weighs. Okay, so another thing I should point out, as you go left to right and down this periodic table, that number is going to get bigger. The lower down on the periodic table an element is, the larger its atom will be. You're adding on more subatomic particles, it's going to get bigger and bigger. And it's going to weigh more. Okay, so let's talk about how we're going to be using these numbers. This little number right here, the atomic number, it doesn't just tell you where it belongs on the periodic table, it tells you how many protons something has. Okay, so this tells number of protons. Okay, so if we look at an element, like if I go to number 23, vanadium, I know exactly how many protons it has. It has 23 protons. Okay, so that little number tells you immediately how many protons something has. Germanium, it's number 32 on here. It has 32 protons. Let's see, californium, number 98, has 98 protons. Any element on here, if you look at its atomic number, that's how many protons it has. All right, now when we're looking at these elements on the periodic table, that is a neutral atom. Right? Depending on how atoms are interacting with each other, they may gain or lose charge. Okay, because electrons can move. Right? If you add an electron onto something, electrons are negative. So you're putting more negative charge on there, and it will make something negative. If you take electrons away, you're subtracting a negative. If you subtract a negative, that gives you a positive. Okay? But if we're looking at these elements as they are in the periodic table, they aren't positive or negative. That means they need the same amount of positive charge as they have negative charge. If you've got something like a carbon, right? So if we look at carbon on the periodic table, it has a 6 for its atomic number. That means that there are 6 protons there. Right? So that's a positive 6 charge from all those protons, because each one of those protons has a positive charge. So if you have 6 of them, you have a positive 6 charge. Okay? But carbon, by itself, doesn't have a charge. It isn't positive, it isn't negative. So we need to get rid of that positive charge somehow. The way to do that is to put some electrons on there. Okay? So if you have a positive 6 charge, and you want to get rid of it, how many electrons would you need? 6. Okay? So this little number here, this atomic number, it tells us our number of protons, tells us how much positive charge the nucleus is giving us. It also tells us how many electrons it has. Because if these two numbers aren't the same, you'll have more positive charge than you have negative charge. And we don't. These are all neutral elements. These are all an equal amount of positive and negative. Okay, so the atomic number, if you look at any element, will tell you how many protons it has and how many electrons it has. So like if you look at nickel, nickel has a 28 as its atomic number. So a nickel atom has 28 protons and 28 electrons. Okay, so That little number tells us a lot. It tells us how much of two of our particles we have. Okay. Now the big number tells us the atomic mass. Okay. Now this is measured in atomic mass units. Okay. So this thing has a mass of 18.998. Okay. Another way to think about this is this number tells you how many subatomic particles are in the nucleus. When you're looking at an atom, a vast majority of its mass is from the nucleus. The electrons are extremely light. The protons and the neutrons are the heavy ones. Okay? Each one of them has an atomic mass of 1 atomic mass unit. Okay, so if we're looking at this right here, this 18.998, that means that on average, a fluorine atom has, rounding it up, 19 subatomic particles in its nucleus. Okay? So this tells us the number of subatomic particles in the nucleus. Okay. Another name for these subatomic particles in the nucleus, these we call nucleons. All right, so think about how these things are named. Proton, electron, neutron, okay? Nucleon, it's got that on at the end because we're talking about a subatomic particle. And then nuclei, that's because it's everything that's in the nucleus, okay? So this is your protons and your neutrons together. Okay. From that, we can kind of come up with a little bit of a simple math equation. Because nucleons that's just your protons plus your neutrons. Okay? So if we wanted to figure out how many neutrons we had, okay, do you have a way of finding how many protons an element has? Yeah, we do. Protons are just whatever your atomic number is. Okay, so in this case, if we're looking at fluorine, we have 9 protons. Okay, so if we turn this into a formula, plug stuff in, all right, so for fluorine, we've got 9 protons. So we're going to plug that in for protons. So 9 plus however many neutrons we have equals how many nucleons we have. Okay, so let's look at this thing again. Our big number tells us our number of nucleons. 18.998. Okay, now these are always going to have like decimal places after them. Rounded to the closest number. Okay, so 18.998, 19. All right, so that number right there, that's how many nucleons we have. I'm going to put that where nucleons are in the formula. So 19, right there. Okay, so if I wanted to figure out how many neutrons I have, it's basic algebra, right? If I've got 19 equals 9 plus the number of neutrons, if I want to figure out how many neutrons I have, I would just subtract 9 from both sides of that formula. And I would end up getting 9 neutrons. Okay? Now, it's obviously not always going to be 9 for each element. This is specifically for fluorine. Let's look at a couple more examples. Okay, so we've got 3 elements up here. We've got potassium, beryllium, and iodine. Now, first thing you may be noticing, potassium doesn't have a K in its name. A lot of those elements are named off of ancient names for them. Like you'll notice that iron is up there with an Fe. There's no F or an E in iron. That comes from an ancient name for it. Ferrous, okay? So a lot of those don't make a ton of sense. That's because you're thinking about them in English, okay? So some of them you're just gonna have to get used to. Like gold is AU, silver is AG. A lot of them are weird. You'll just have to learn how to find them. We'll talk about more trends on the periodic table that will help you find them in a later video, okay? But after a year of looking for them, you'll get pretty good, all right? So we got potassium up here, all right? Let's say that we're looking for our number of protons, electrons, and our neutrons. Okay, so our protons and electrons, those are both really easy to find because it's just your atomic number. Okay, so we've got a 19 right there for potassium. All right, remember, the atomic number is the numerically smaller number. If you're looking at a different periodic table, these numbers may get switched, but you're still going to be looking for the small number. Okay, so now protons, atomic number. We have 19 protons. Okay, if this thing is neutral, that means we have the same amount of electrons and protons, so that means that our electrons would also be 19. Okay, last one, neutrons, the one that requires a teensy tiny little bit of work. Okay, if you look at potassium, it has a total of 39 nucleons. Okay, so we've got a total of 39, and 19 of them are protons. Okay, so using our little formula, all right, so nucleons equal our protons plus our neutrons. Okay, the nucleons, that's the 39, that's our atomic mass. So 39 in there. Our protons, we already found that, that's 19, plus our number of neutrons. Okay, little teensy tiny little bit of algebra. 39 equals 19 plus our neutrons, so to figure out how many neutrons we have, we're just gonna subtract 19 from both sides. That 19 goes away, and what's 39 minus 19? Okay, so this thing has 20 neutrons. Okay, one trend that you'll end up seeing when you're calculating your neutrons, for elements at the very beginning of the periodic table, so at the top, the number of neutrons is going to be very close to the number of protons and electrons. Always larger, but close. Okay? Once you get lower down on the periodic table towards the heavier stuff, the number of neutrons is going to spike. The reason for this is because when we're looking at an atom, I'm going to draw a picture of it real quick. We've got our atom right here, we've got our little electrons flying around. Okay? Think about what is in the nucleus. Protons and neutrons. Okay? Protons are positive. Every single proton has a positive charge. So think about how tightly packed they are in there. All these positive protons. You ever take the north end of a magnet and try and put it next to the north end of another magnet? They repel each other. Same thing happens with these charges. If you have two things with a similar charge, both positive or both negative, they'll try and repel each other. So think about that. All those protons packed into a little tiny space, all trying to repel away from each other. But this nucleus sticks together. There has to be a reason why. And the reason why that people have found is because of those neutrons. They emit what's called the strong nuclear force. It doesn't act over a very long distance, but it is extremely strong, strong enough to overcome the electric repulsion between those protons. Okay, so neutrons are kind of like the glue of the nucleus. Okay? But there's an issue with that. Strong nuclear force does not go over a very large distance. So as you start getting to elements that are bigger and bigger and bigger, those neutrons aren't close enough to each other. They're starting to spread out because you're fitting more and more of these subatomic particles in a space, and they need to expand. They can't like occupy the same space as each other. So if you're looking at something like a gold nucleus compared to a hydrogen nucleus, where did I put that periodic table? Okay, so hydrogen has an atomic mass of 1. It's just one proton. Has a little tiny itsy bitsy nucleus. Gold has an atomic mass of 197. That's 197 particles all packed into a space. Okay? So that nucleus is significantly bigger, and it's getting bigger to the point that the neutrons aren't going to be able to hold it together anymore. It's getting so wide that it's starting to crumble apart. Okay, so if we look at elements after about lead on the periodic table, that's when you start getting things that are radioactive. Radioactivity means that the nucleus itself can't hold itself together. It's unstable. It's going to fall apart. It's going to break off little pieces in different types of radiation. Okay, so if you start looking at the ones really low down, like samarium, has 150 as its atomic mass, but only 62 of that is protons. That's a lot of neutrons trying to hold this thing together. The bigger it gets, the harder it is to hold together. Okay, so as you go down on the periodic table, you're going to see a lot more neutrons. All right, up towards the top, you'll probably have the same amount of neutrons as you have protons and electrons. Like, this is super close. You only have one more neutron than you have electrons, or than you have protons. Okay, smaller atoms don't need as many neutrons to hold themselves together. Okay, next one, let's look at beryllium. Now, this is another small one, so our number of neutrons should be pretty similar to our number of electrons and protons. Okay, let's look at our pieces. Protons, that's just our atomic number. So in this case, beryllium is 4. Electrons, atomic number again, 4. Okay, and then the last one, neutrons. Okay, so the way to find that is just take your atomic mass and subtract your atomic number. So 9 minus 4, we have 5 neutrons. Okay, whenever you're looking for your number of neutrons, it's just going to be your atomic mass minus your atomic number. Take the big number and subtract the little one. Okay, last one, iodine. Now this one's a lot lower down on the periodic table. All right, all that other stuff was up here. Now we're down towards the bottom for our iodine. Okay, so this one is going to have a lot more neutrons compared to its protons and electrons. All right, so if we're looking at this one, our protons, still easy to find. It's still just our atomic number, so 53. Our electrons, also our atomic number, still 53. Okay, and then last, our neutrons. Okay, so remember our formula for that. We've got an atomic mass of 126.9, so that rounds up to 127. All right, and that is equal to our number of protons plus our number of neutrons. So 53 for our number of protons plus our number of neutrons. Okay, so if we want to find how many neutrons we have, we're just going to subtract that over. So 197 minus 53, that gives us 74 neutrons. Okay, so you'll notice this number's bigger. All right, as you go further and further down on the periodic table, your number of neutrons will increase. Okay, and that's just because you've got such a big nucleus, it takes a lot of neutrons to try and hold that thing together. Once the nucleus gets too big, it's going to start falling apart, and that's how we get radioactive elements. Okay, so on today's assignment, it's all about finding these numbers. How many protons do you have? Look at your atomic number. How many neutrons do you have? Look at your atomic number. Sorry, how many electrons do you have? Look at your atomic number. How many neutrons do you have? Look at your atomic mass and subtract your atomic number. Okay, so if you have any questions as you're going through, make sure that you message me on Schoology or send me an email. I would love to help. All right.